Welcome back to Topics in Statics. Today we're going to talk about vectors in 3 dimensions. We've covered vectors in 2 dimensions. 3 dimensions is just more of the same. Things are just a little more complicated because there's more things to keep up with. First thing to note in 3 dimensions is we have to have a right-handed coordinate system. The reason is that all the mathematics of vectors is defined in terms of right-handed coordinate systems, so you have to make sure you have a right-handed coordinate system. I'm not going to go into detail about all this. Look at the picture, read what the words say there, check your coordinate system. So the first thing we have to do if we're talking about a vector in a coordinate system is we have to be able to resolve the vector into its components. In this case, there'll be 3 components, x, y, and z. So here in this figure, we've got a vector A, the blue arrow, and it's easy to find the component in the z direction. It's how high up this thing is. But then I draw this triangle. Let me shade in this triangle maybe. That would help. Here's this triangle up here. This is the triangle I'm looking at. I can use that triangle. It's a right triangle. And I can break the vector up into 2 components. And those 2 components are going to be the z component. And the second one, this side over here, is what I called A prime. Right? It's some length, but it's not parallel to either x or y. I can drop it down. It's in the xy plane, but it's not parallel to either x or y. So the first thing I do is I do just like I did with 2-dimensional vectors. I break this vector A up into 2 components, AZ and A prime. Then I have to break up A prime using a different triangle. So now I go down here and I'll use maybe this triangle. And I break A prime up into x and y. And so when I put it all together, I end up with the magnitude of A is ax plus ay plus az. Right, each of these 3 component vectors can be written as a scalar times a unit vector. In 3-dimensional coordinates, my standard 3-dimensional Cartesian coordinates unit vectors are I hat, j hat, and k hat. So now I can do a little vector algebra. I'll just start off by telling you that the magnitude of a vector in 3 dimensions is I have to square each of those components, add them together, and take the square root. So now I just play a little games with algebra. I start off, I write A is equal to ax I hat plus ay j hat plus az k hat. So I really want to write this as a magnitude times a direction. So I'm going to multiply by the magnitude, but I can't just multiply by the magnitude. I can only multiply by 1. So I multiply by the magnitude divided by the magnitude, A over A, times that what I just said. Then I take the A in the denominator and distribute it throughout the parentheses there. So I've got a magnitude on the outside, and then I've got ax over A, I hat direction, plus ay over A, j hat direction, plus az over A, k hat direction. Well, what are all those things in there? That's how I calculate a unit vector. That's by definition, that's what a unit vector looks like. That's what a unit vector is. So there it is. That's how I find the vector A is equal to the magnitude of A times a unit vector in the direction of A. Right, I can go back and do a little bit more with algebra. I can define 3 angles. These 3 angles are each between the vector A and the 3 different coordinate axes. So the vector, or the angle alpha, is between the vector and the positive x-axis. The vector beta, or the angle beta, is between the vector and the positive y-axis. The gamma is between the vector and the positive z-axis. All of these angles have a value somewhere between 0 and 180 degrees. And so I can find the components of the vector using the following relations. That the cosine of alpha is ax over a. The cosine of beta is ay over a. The cosine of gamma is az over a. Those numbers are called the direction cosines of a. Well, I can keep going. Ax over a I hat plus ay over a j hat plus az over a k hat, that's just the unit vector in the direction of a. So from the direction of the cosines, definition of the direction cosines, the unit vector is cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. And I know that for any unit vector, its magnitude has to be 1. So if I take each of those cosines and square them, add them all together, it better be equal to 1. Another way to look at this is with what are called transverse and what your book calls transverse and azimuth angles. This gets really confusing because depending on where you look, those names mean different things. Transverse and azimuth are not universal definitions. So I'm just going to refer to them as theta and phi. And so I'm going to show them to you on this picture. This is the original picture where we took the vector A and broke it up into components. But now I'm going to define these angles. Here's one angle, the angle theta, and here's the angle phi. So using that triangle, that upper triangle with the phi, I can resolve the vector A into two components. AZ is a cosine of that angle phi, and A prime is a sine of phi. But then, just as we said before, we have to break up A prime. And so AX and AY, I look at this lower triangle with the theta in it. AX is A prime times cosine theta. AY is A prime times sine theta. So then I put all that together and I get the result there. AX is A sine phi cosine theta. This is not something to memorize. This is something to understand where I got those numbers from, how I resolved it from this picture. Because you're often going to be given a picture with those two angles, and you have to resolve it into its components. So practice this. It'll make more sense later. So addition of Cartesian vectors, it's just like adding vectors in 2 dimensions. You add like components. Yeah, I don't have a whole lot to say about that. A lot of this will make more sense as we go along. We'll work problems in class, and you'll understand how to better resolve a 3-dimensional vector from looking at a picture. Next time we're going to talk about locating points in space. It's important to be able to create our own vector depending on locations in space, and that's what we'll do next time. Till then.